Also, objective of this lesson is to understand the basic concepts of related rates. Now, the first question that comes to our mind is, why do we call this as related rates? Now, when you refer a simple example, now if you look at the first thing is that, for example, if area of a circle is pi r squared. Now, what happened is that if let's say the area is changing with respect to radius. Now, in a point where I don't care about the time factor, my area that is changing with respect to radius is actually given by dA by dr, which is 2 pi r straight away. Now here there is no constraint about the time. Now actually just like, okay, now suppose there is a circle. Now here at any stage, the rate of change of area with respect to radius is linked. But there is no link of at what rate the radius is changing and at what rate the area is changing with respect to time. Now, if I ask you here in this question that, okay, find out the rate of change of area of the circle when radius is 2. So you will say, okay, rate of change of area of the circle with respect to radius is actually 2 pi times 2, which is nothing but 4 pi. But actually, what happened is that if I induce another factor here, if I, let's say, take a consideration of a simple example here, assume that you have dropped a stone in steady water. So when you watch that, the ripples around this point keep spreading. So when you see that the ripples around the points are spreading, they go at certain rate. Okay, so the spread is at certain rate. Now that is nothing but at what rate my radius is changing. Now at the same time, your area is also changing. Area of each ripple that is formed is changing. So related rates actually helps us understand the link between two quantities. So how area can be related with respect to radius. And the third factor that counts is nothing but the time. So the area with respect to time, radius with respect to time. So the related rates is between two quantities. Now, for example, let's say here in this example, if I take differentiate with respect to time, so my left hand side actually is dA by dt. So the actual significance of this is at what rate area is changing with respect to time. And at that time, my answer will be actually in terms of radius. At what rate my radius is changing with respect to time. So at what rate the radius is changing. So at what rate radius is changing. Radius is changing. That's a crucial question. So related rates actually help us link two different quantities with respect to time parameter. Now, the process is very, very simple. The process I'm going to teach you very, very easily. Hopefully, with this examples, it'll be clear. Now, the answer here is if you know a little bit about different implicit differentiation, that's what is going to help you. Now, how I link up with it? Let's say in this case, if I say dA by dt, I can say, okay, dA by dt can be written as dA by dr times dr by dt. Because anyway, you can see that if you consider the simple cancellation law here, it gets cancelled. But actually, it has got to do with little more aspect. The bigger aspect is at what rate your area is changing with respect to radius times at what rate radius is changing with respect to time. So the link of time area with respect to time is actually here is given little bit in terms of radius. So in this case, the answer is dA by dt is going to be 2 pi r, because that's what is my dr. d 2 pi r times dr by dt. Now, this is the relation in at what rate area is changing with respect to the radius of the circle and with respect to time as well. So if one of the quantities is known to me, let's say I know that, okay, the radius is increasing at a rate of 2 meters per second. And at an instance when radius is 5, my area will change at a rate of 2 pi times 5 times 2 assuming this is radius is 5 meters. So it is going to be increasing at 20 pi meters square per second. So this is how you calculate the unknown parameters. So if you know one of the things, you can find out the other things. Now I just wanted to emphasize on this part here. This is the part which students find difficult. Now this part actually is a very logical one, which is very you can generalize a way to do it. Now what I actually understand is that if I have to differentiate, let's say, any two variable with respect to time, let's say I have got pi times L cube. It's a random relation, it's not linked with this problem. Now I wanted to introduce a time factor here. Let's say at what rate volume, or let's say V changing with respect to time, with respect to L, with respect to time. So when you introduce here dV by dt, actually you could just differentiate L cube like normally you do. Okay, so it is pi times 3L square. But since you differentiated L, just don't forget to multiply by dl by dt. And this is much more easier. That okay, you differentiate this expression normally and just multiply it with whichever variable you differentiated with respect to time. Now, another example, let's say volume of a sphere is 4 over 3 pi r cube. And I wanted to introduce the time factor here. So I wanted to introduce the time factor, which is dv by dt here will be 4/3 pi, that is constant. I would just differentiate r cube, which is normal, 3r square times, and I differentiated r, so that's just dr by dt. Now these are actually the straightforward methods, but actually if you see what I did out here is, I actually did this, dv by dt is dv by dr times dr by dt. And dv by dr is actually this part, which is here, and dr by dt is this. So now if I collectively take a simple example, let's say, that is, if you have got a function, let's say y equals to f of x, I would simply say that if you want to induce a related rate here, you just do dy by dt is f dash x times dx by dt. So there is nothing to get confused with. Okay, I do normal derivative here for this and just multiply with the variable you're differentiating. If your variable is, let's say, z equals to f of L, okay, if you wanted to induce related rates, dz by dt will be f dash of L times dl by dt, because I differentiated L. So let's take some examples on this concept. Now, the first example that I really like giving is in terms of the volume of sphere itself. So assume that there is a sphere whose surface area and volume formulas are given by 4 pi r square, and volume is given by 4/3 pi r cube. Now it has been given that due to heat it is expanding. Due to heat it is expanding, the radius is increasing at a rate of 0.2 meters per second. Now at an instance, when radius is 10 meters, what is rate of change of volume and surface area? Rate of change of volume and surface area. So let us have a look at this relation first. So surface area is given by 4 pi r square, and so my ds by, now because I'm asking at rate of change of volume and surface area, so rate of change of quantity is related with time. So ds by dt, as I said correctly, that okay earlier, that 4 pi r square, you do normal derivative. So 4 pi times 2r, but you differentiated variable r, which is dr by dt. That's how I remember it. And now the next step, you just plug in and substitute the correct values. So when I look at dr by dt, it is 0.2. And when I look at the radius, all right, radius is 10. And you get the ds by dt. So you just put in the values, 4 pi times 2 times 10 times 0.2, and you calculate this answer. Now coming to the volume fragment. So volume is basically 4/3 pi r cube. Now volume dv by dt here, if I do, is 4/3 pi times r cube. If I differentiate, it is 3r square, normal derivative. Because I differentiated r, I love to do dr by dt here. So I did normal derivative. This actually is dv by dr. Okay, and then you substitute the values here. So 4/3 pi times 3 times radius is 10 square times dr by dt, which is 0.2. And then you calculate the exact answer. So this is a basic concept linked with the related rates. And let's take some more challenging problems on this concept. So well, here is another example on how to do the related rates concept in real life problems. Now, a ladder 10 meters long is leaning against a vertical wall, and now with its other end on the ground. The top end of the ladder is sliding down the wall, and when the top end is 6 meters from the ground, it is sliding at 6 meters per second. How fast is the bottom moving away from the wall at this instant? So let's take the problem in, let's just draw approximate diagram for this. So the diagram of this approximately look like, so a ladder is 10 meters long. So the ladder is 10 meters long. So I'm just going to draw a surface here. This is the wall, and here is the ladder approximately. So the ladder is around 10 meters long. So in this case, this is 10 meters long, and what we got is this. So when the top end is 6 meters from its ground, when the top end is 6 meters from the ground, so this is at an instant 6 meters from the ground, it is sliding down at a rate of 2 meters per second. So this end is coming down at 2 meters per second. So find how fast the bottom edge is moving away from the wall at this instant. So now in this case, what we got to do is we got to first relate the two quantities. Which two quantities actually are changing here? So if I look at this is x, and if I put this is y, so actually what's happening is here, first I got to set up the relation, that is your x square plus y square equals to 10 square. That's your relation, because the length of the ladder is always constant, irrespective of wherever the position of the ladder comes in. Let's say ladder is here, the length of the ladder is still going to be the same. Or you're here, let's say, for example, and then that matter, the length of the ladder will be still the same. So the length of the ladder is not changing. So at this stage, what we do is, this is our interesting fact and the general assumption that we made for x and y to get a relation in x and y and the length of the ladder. So now the next step is, how do we introduce the related rates here? You got to just simply differentiate both the sides with respect to time. So when I differentiate with respect to time both the sides, the derivative of x squared is 2x, and because I'm differentiating with respect to x, it is times dx over dt, plus y squared is 2y times dy by dt equals to 0. Now here I'm just making it very simple. You just differentiate normally, x squared derivative is normal, and you differentiated x with respect to time, so it's just multiply by dx by dt. Similarly, you find out y squared derivative is 2y times dy by dt. So what we get eventually here now, what are the values given to us? So at instance when it is 6 meters from the top, okay, so at that instance, what is the x value? So 6 square plus x square equals to 100. The x square is 100 minus 36, which is 64, which gives me x as 8. So at that instance, my x value is 8. So 2 times, now I'm just going to put the values here. So it is going to be 2 times 8 times dx by dt plus 2 times y. Now y is 6 meters. And now since it is coming down, you would like to write this as negative. So negative 2 meters per second is dy by dt, and equate to 0. So dx by dt from here we get is negative 12. So 6 fours are negative 24 over 16. So this is the rate at which basically the ladder is going towards the right. It's coming positive, you can see. Hence you can see that rate at which the ladder is slipping is that value.